Okay, we are at 29.5, Gauss's law in magnetism. Let's share the PowerPoint. Gauss's law in magnetism. If you recall, whenever we define an area or a dA or an area vector, the magnitude is equal to the area, but the direction is perpendicular to the surface of the area. It's perpendicular to the surface. So you can see the little dark colored dA, the little portion of the area is coming out perpendicular from the surface. So that is true no matter where you are on the surface. On any part of the surface, there's going to be a vector coming out. There's going to be a vector coming out that is perpendicular to the surface no matter where you are on the surface. And the B is going to be making an angle theta with the perpendicular to that surface. So the magnetic flux is equal to the integral of B dot dA, which is BA cosine theta. That's a dot product. B dot dA, BA cosine theta. So the magnetic flux is equal to BA cosine theta. Now, the flux, if we look at A here, the flux through the plane is 0 when the magnetic field is parallel to the plane surface. So here, dA, remember A is the magnitude of the area, but the direction of A, vector A, is perpendicular to the surface. So B dot A, BA cosine theta, the cosine of theta here is, theta is 90, so the cosine of 90 is equal to 0. So the flux through the plane is, there is no flux. You can just see the lines are going, they're not intersecting the plane at all. However, let's look at B. The flux through the plane is a maximum when the magnetic field is perpendicular to the plane. Because here, theta between B and A is equal to 0, and the cosine of 0, remember, it's B dot A, and so that's BA cosine theta, and the cosine of 0 degrees is 1. So that's the maximum. Anywhere in between, if here's your magnetic field and here's your surface, it's going to be a cosine. It's going to go from 0 to 1. So it can never be greater than 1. Okay, and the term for flux is Webers. 1 Weber equals 1 Tesla per square meter. 1 Tesla per meter squared. Okay, now the magnetic flux through a closed surface surrounding one of the poles or any other closed surface is 0. In other words, you've got as many flux lines coming into the surface as you do going into the surface. We should recall there was a similar effect for electric flux. If you have a charge inside a closed surface, it's just equal to it's related to the charge inside. But if the charge were outside the closed surface, you've got electric field lines going into the surface, but also coming out of the surface, so that the total was equal to 0. Here it's the same with the magnetic field. You've got magnetic field lines going into the surface, but then magnetic field lines coming out of the surface at the same time. So the net magnetic flux through a closed surface surrounding one of the poles or any other closed surface is 0. So the net magnetic flux through any closed surface is always 0. The integral of B dot dA equals 0 for a closed surface. Okay. The magnetic field lines resemble those of a bar magnet, meaning that the solenoid effectively has north and south poles. And that pretty much, I'm going to, for the sake of time, I'm going to skip section 29.6, magnetism and matter. I may come back to it later, but for right now, well, I'm just going to publish these lectures, or I'll make it an extra assignment.